Alrighty. The next couple of videos, we're going to talk about periodic trends. I want to start off here with atomic and ionic radius. Um, this is a way to think about what the size of these atoms and ions are. Um, so, and this bleh, this can vary uh, depending on, you know, what kind of measurements were done uh, to figure out what the radius is. So different things are measured differently. So maybe it's the distance between two nuclei in a solid compound, or maybe it's the bond length between two atoms in a molecule. But there's lots of ways to do it. A lot of this we're just going to refer to the average radius, which would be the average of all the different radii that are formed from different measurements. Okay, we're not going to stress too very much about the actual data. We're just going to think about the trends in general. Okay, and then hopefully our goal is, can we compare things based on their size, and can we explain why the trends are the way they are? Okay, when we look at ionic radius, we really see not ionic radius, atomic radius, we really see two things, and we're focusing on the main group because, as we've said before, transition metals are weird. Um, the first one is easy to get. As you go down the periodic table, down the group, okay, the atoms get bigger. They get physically larger, right? The orbitals are bigger. There's more protons, neutrons, electrons. They're just physically more of them, okay? So, and that holds true for every group as you go across, okay? The trend that's not intuitively obvious is as you go across the group, and I always think of it going from left to right, okay? They're doing the trend from right to left. But as you go across the group, the radius decreases, the atoms get smaller. And this is the one that's not intuitively obvious, okay? If we think about it, oops, let me go back. If we think about it, um, right, as you go down, you're adding more stuff, but as you're going across, you're adding more stuff, okay? This, again, is going to be a job for effective nuclear charge, okay, which is also known as Z effective. That looks like ELF, effective, ZEEFF, okay? So if you think about it, as you go across the period, you're adding in one proton and one electron for every atom. Okay, not too terrible. But while you're adding protons to the center, you're adding electrons to the outside. Okay, remember the core electrons are what's shielding the outer electrons from the nucleus. The outer electrons don't do much shielding at all. So what we're doing is we're increasing the positive charge in the center, but not increasing the shielding. And so the effective nuclear charge is increasing. So our effective nuclear charge increases left to right across the table. Because the charge is increasing, the outer electrons, which is really how we're telling our size, the outer electrons are held tighter. Okay, because the outer electrons are held tighter, they get pulled closer to the positive charge. Okay, and that makes them smaller. Okay, so that's kind of our thought process here. We're going to increase the effective nuclear charge. That means our outer electrons are held tighter, so they're pulled closer to the nucleus, and being closer to the nucleus means that our atoms are physically smaller. Okay, one thing we need to be able to do is, can we determine, maybe we can rank or we can identify the smallest and the largest. And when we say the smallest and largest, we're meaning atomic radius. Okay, and we're going to think about this through a lot of different trends in the next couple of these. Okay, so we're going to compare sulfur, calcium, fluorine, rubidium, and silicon. Okay, so task number one is to find them. Okay, there's sulfur, calcium, fluorine, rubidium, and silicon. Okay, remember our trends. And it's all right to doodle this. I see this all the time. People will doodle in the margins on their exam or whatever. So this gets big and this gets small as you go across. So the smallest one should be the furthest to the right and the highest up. So the smallest should be up here and the biggest should be on the bottom left. Okay, you can think of it as the radius increases along the diagonal. So here, fluorine should be the smallest, right? The one that's most to the left and most down of this set is rubidium, the largest. And let's just go one step further and see if we can rank the rest of these. As we move through the diagonal, right, fluorine, then sulfur, then silicon, bing, 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 and then calcium's way over here, and then rubidium, right? So the radius increases through that trend as we go, okay? When we're thinking about ionic radius, we have to take in a couple of things into account. One of those is whether or not it's a cation or an anion, okay? And we have to also remember that the atomic radius trend still holds true. So as you go down the group, the atoms get physically larger, okay? So as you go down the group, if you're comparing things that are the same group with the same charge, the atoms will get physically larger. So F minus, Cl minus, Br minus, I minus get larger as you go down. Li plus, Na plus, K plus, Rb plus get bigger as you go down, okay? Where we're going to start with this, though, is we're going to say that cations are smaller than the neutral atom where it came from, okay? And this is because of there's increased effective nuclear charge. You're taking out that outer electron, and you haven't really shrunk down the center. So you've lost the outer bits, and all you have left is the core, and the core is physically smaller, okay? And that's true for every cation that's there, okay? Oh, crap. I'm sorry. Go back. I forgot what I'm doing. Okay. So, okay. It says it right here. Dang it. More positive charge is smaller. That doesn't matter in the main group, but for uh, transition metals, it does make a difference, right? So an iron 2 plus should be bigger than an iron 3 plus because more positive charge makes it smaller. And again, that is an increase of effective nuclear charge. Effective nuclear charge is everywhere, okay? If we look at the other way around on this, if we look at anions, anions get larger than uh, the atoms they came from, right? So if you look here, the phosphide, the P3 minus is much bigger than a phosphorus. S2 minus is much bigger than sulfur. Cl minus is much bigger than that. This is a decrease of effective nuclear charge. Is it? Yes. Okay. Because the electrons can get farther away. They're held by fewer things, right? So in O2 minus, we have 10 electrons, but there's only 8 positives. Fluoride, we have 10 electrons, but there's only 9, right? Neon, right? But the atomic trend still holds true. As you go down this way, I feel like I'm missing a slide. As you go down that way, the atoms still get smaller. Okay. And if I remember right, then there's nothing here, right? Okay, so we'll do it here. One other set we have to worry about here is if you have isoelectronic series. This is an example of an isoelectronic series. Right? Remember, isoelectronic means they have the same number of electrons. Sometimes they even go further and say the isoelectronic means they have the same electron configuration. Okay, but here all these have 10 electrons. Okay, but they have 8 protons, 9 protons, and 10 protons. These are isoelectronic. If they're isoelectronic, that just means that the more protons is smaller. Okay, and that holds true as we get cations as well. So if we look here, I guess with this figure's already got them highlighted. The nitrogen, oxygen, fluorine, sodium, magnesium, and aluminum are all isoelectronic to the same noble gas, which is neon. Okay, all of these things have gained or lost electrons to get 10 valence electrons. That's the stable neon noble gas core. The anions are larger than the atoms that they came from, and the cations are smaller than the atoms that they came from. But the trend in this series is as you have more positives, more protons in the nucleus, the ions get smaller. Okay, and this is again completely due to effective nuclear charge. Okay, so there's lots of ways to think through this. I think of it as if you're looking at a set, just make sure it's isoelectronic, or make sure it's going down a group and all the charges are the same. Okay, or it's going to be the same element with different charges. Those are really the only three things we can compare this way. Um, but if there's an isoelectronic set, then anything that has a more positive charge is going to be smaller. And the trend would be, say, like a 3 minus is the largest, then a 2 minus, oops, then a 1 minus, then a 1 plus, then a 2 plus, then a 3 plus. Okay, so think that through. Look at some stuff and practice ranking them, um, and let me know how you go.